Hello folks, here is a common example problem where energy conservation is super useful. Here's the question. A person sleds down a frictionless hill of vertical height, capital H equals 15 meters. What is their speed at the bottom of the hill? What's interesting is, in the end, is that that's the only piece of information you need is the height of the hill. Let's draw the picture, draw an LOL chart, and see what we can do. All right, so here we are. We've got our person on the sled, and they are ready to go down this hill whose vertical height H is 15 meters. All right, how fast are they going at the bottom? So that's the question. Here at the bottom, they have a certain speed. What is that speed? And we'll assume that they start with an initial velocity of 0. They start at rest. All right, let's draw an LOL bar chart. How would I know, if this weren't the energy chapter, to use energy conservation? That's a great question. One big hint is that I don't have any time information in the wording of the problem. All I know about is position and how the position changes. That's my big hint that energy will be useful. My system here, I'm going to choose to include the Earth and the person in my system, and they could have kinetic or gravitational potential energy or spring potential energy, kinetic, gravitational potential energy, spring potential energy. I'm going to leave friction off of my L because it's a frictionless hill, and I ran out of room is the real brief. Actually, you know what I'll do? I'm on a tablet here. So we'll just move that over a little so that we can make some room for that delta E therm addition. All right. Person starts at rest. I'm going to choose my reference height of y equals 0 to be the bottom of the hill. And now I can meaningfully say that there is initially gravitational potential energy to start off, and there's no stretchy or compressy thing. There's nothing outside of the system, so there's no working being done to add energy into or out of the system. The person is moving in the final scenario, but they're at my reference height. Nothing is stretching, and it was a frictionless hill. So the 4 blocks of gravitational potential energy become 4 blocks of kinetic energy in the end. As an equation, this says that the gravitational potential energy in snapshot A is equal to the kinetic energy in snapshot B. All right, and now we can use this to compute the speed at the bottom of the hill. We haven't really used this equation much yet, but gravitational potential energy can be determined with mgh. Remember, each of these makes someone more scared when you're holding a bowling ball above their head. Hold it up higher, hold it up hold up something that's heavier, or hold up something in a stronger gravitational field. That continues to be scarier. Kinetic energy is half mass times speed squared. All right. We notice that each term has mass in it. So we can divide every term that's there by mass. Mass divided by mass equals 1. And we're left with g times h equals 1/2 v squared. We multiply each side by 2. We end up with 2gh equals v squared. That came from multiplying each of these by 2. Half times 2 is 1, right? And then in the end, my last step is to take the square root of both sides, and I end up with speed equals square root 2gh. And this is basically the answer, right? This has what I'm looking for, speed, written in terms of what's measured, h, and the gravitational field. So we can see that we can go ahead and compute the speed. For this particular problem, g is 9.8 newtons per kilogram. H is 15 meters. We're taking the square root of all of that. Overall, our speed is, I should have had this ready ahead of time. Give me just a second to type it in. Square root of 2 times 9.8 times 15 equals 17.1 meters per second. And there we have it, folks. We have the speed of the person at the bottom of the hill. I want to highlight a few things. One, at this step here, mass divided out. So this is independent of mass, the speed. Which is amazing. That says that on a frictionless hill, a baby going down that hill and then a fully grown human adult going down that hill would have the same speed at the bottom, which is incredible. It doesn't matter how much mass there is. No matter who the person on the sled is, their speed at the bottom, 17.1 meters per second. Why is that the case? Has to, again, do with the equivalence of gravitational mass and inertial mass. Here, there's more gravitational mass. So gravity is pulling, there's more energy stored in gravitational potential energy. But here, there's more inertial mass. There's more resistance to accelerating. And so those effects cancel out, right? More total energy, harder to get that energy into kinetic energy. So in the end, we end up with the same speed regardless of the person's mass. All right, and there we have it, folks. If you have any questions for me, please let me know.